audible? Hello. Okay, we'll start the today's session. So, in the last week, the lectures were on the topics bonding time, and we had some problems related to the green Ampt infiltration. Then we moved over to the from the subsurface flow. We moved over to the surface flows and SES curve number method and different types of the surface flow phenomenons were covered, like saturation excess overland flow, infiltration excess overland flow. These were covered. So today we'll be solving some problems related to the last week content. So we'll be solving some questions related to the green Ampt infiltration equation and how to calculate the ponding time. So here we'll be seeing how to estimate the ponding time for Horton's model. So ma'am would have covered how to estimate the ponding time for the green Ampt infiltration model. So we'll be seeing how to find out for the Horton's model, and we'll be seeing some problems related to the SES curve number method, and finally we'll be seeing how to estimate the phi index. And this question, the last problem, will not be a very conventional problem. Here there is a little bit of complication involved, so we'll be seeing one by one. So this is the first question, which is related to the green Ampt infiltration equation. So here a rainfall hydrograph is given. So you have a variable rainfall happening for every time interval, and the table is given. So in table we have the incremental rainfall, and if this rain falls on a sandy loam of initial moisture content equal to the field capacity. So your initial moisture content is given as equal to the field capacity, and we need to determine what is the excess runoff hydrograph using the green Ampt approach. So we'll be finding out the hydrograph, subtracting your infiltration, and we need to calculate total initial abstraction, and we also need to calculate what is continuing abstraction and the rainfall excess for the given rainfall event. And finally, you have been given the soil parameters. So Ks is the saturated hydraulic conductivity, and N is your porosity, theta E is the effective moisture content, and theta Fc is the field capacity. And the suction head, which is the negative head, that is given as 11.01 centimeter for the sandy loam soil. So we'll see how to approach this problem. So before going into the problem, we'll just brush up what is the ponding time. So ponding time is the time that is elapsed between the beginning of the rainfall and when the water begins to pond on the surface. So initially your rainfall intensity may be less than your potential infiltration rate, and after certain time your soil begins to saturate and your potential infiltration rate decreases with time, and after a certain point of time your rainfall intensity will be more than the potential infiltration rate. So that is the condition where your water will start to pond on the soil surface. So before ponding, your potential infiltration rate, your rainfall intensity is less than or equal to the potential infiltration rate, and after ponding your rainfall intensity rate will be greater than your potential infiltration rate. So by using this, we would have derived the ponding time for Horton's equation. So the ponding time for Horton's equation was derived by Main and Larson. So here we have three assumptions involved. So the first assumption is for time less than your ponding time, we are assuming that all the rainfall is infiltrated. And the second assumption is that your potential infiltration rate is a function of the cumulative infiltration depth. And the last one is when the rainfall intensity exceeds your infiltration rate, ponding occurs. So these are the three principles which is behind the Main and Larson method to derive the ponding time for Green and Ampt model. So here, so we know the Green and Ampt infiltration equation. So here, your infiltration rate is equal to hydraulic conductivity into 1 plus psi delta theta divided by F. So this is the Green and Ampt infiltration rate equation. So here, when the ponding occurs, we have your infiltration rate will be equal to the rainfall intensity, and your cumulative infiltration depth can be written as rainfall intensity into time of ponding. So if we substitute in this above equation, so your F is equal to I, this is K, psi delta theta will be as it is, and ITP. So we need to derive the expression for time of ponding. So time of ponding will be equal to K psi delta theta divided by I into I minus K, and provided your rainfall intensity is greater than your saturated hydraulic conductivity. So this is the Main and Larson equation to calculate the ponding time. This will be applied in the Green and Ampt equation.
Sir, what is I here?
I is the rainfall intensity. Here I is the rainfall intensity. K is the saturated hydraulic conductivity. So now we'll be moving to the question. So in the question, table is given with the incremental rainfall. Uh, so first we'll be calculating. So first we'll be estimating the parameters which are required for calculating the cumulative infiltration depth for each time period. So we need to estimate what is psi delta theta first. So
Sir, excuse me, sir.
yeah,
Sir, can we have the access to the recorded video of the past lectures?
yeah, it is available in the YouTube channel. I will share the link of that.
Okay, okay, sir. Thank you.
Yeah. So here first we need to estimate psi delta theta, and for that we need to know what is delta theta. So delta theta is given by the expression 1 minus your saturation into your effective moisture content, and we would have derived an expression for the to find out what is the saturation. So that is given by your initial moisture content minus the residual moisture content divided by the effective moisture content. So here we are given a condition. We need to take the initial moisture condition equal to the field capacity, and your field capacity for the given soil is 0. 0.2586. So this is given in the question. And for this soil, theta r is given as 0.041. And theta is given directly in the question. So we'll be estimating what is your effective saturation. This is 0.412. So this equals to 0.528. Now we can calculate what is delta theta. So 1 minus 0.528 into 0.412. So your delta theta is 0.1945. Now we can find out what is psi delta theta. Psi is given as 11.01 multiplied by 0.1945. So your psi delta theta is equal to 2.1414 centimeters. So now we have calculated what is psi delta theta. So I'll just write down what is the uh, rainfall and the time which is given.
Sir,
Yes.
sir, in the question that was given in the assignment, there is a range of answers. Like my answer in one question is like 10.43,
Okay.
and it got rejected because of the answer is in the range 10.53. Sir, it is 53.
So this happens because while solving your question, in the question it will be given like approximate your answer to two decimal places, three decimal places. So when you are solving in calculator, try to solve it as much accurate as possible. Don't round off in between. Like if you see here, I have found out AC to be 0.528. So don't round this up to 0.53, and later you find delta theta, and here you don't round it to 0.195 like that. So this successive approximation which you do in multiple steps will result a little bit changes in your answer, and finally it might go out of the range.
Yes, sir. Yes, sir.
So while solving, you solve it as much precise as possible, like 3 to 4 decimal places, and the final step when you round off carefully. So that is that which you need to keep in mind.
Sir, there is one more doubt, sir. Sir, don't we have we called watershed boundary as a catchment another name?
Watershed boundary, catchment, they are all similar. Only the scale will be different. They are
Sir,
all
but in assignment one, I marked all the options as correct name of watershed like catchment, but in the answers that was given, it like watershed boundary is not the answer of the another name of catchment.
okay. We'll check out what is that. We'll see.
Okay, sir.
So now we have written down what is the time and the incremental rainfall. Now we'll go on to how to calculate the infiltration rate and the cumulative rainfall depth in each time step. So we know that infiltration rate is given by F is equal to saturated hydraulic conductivity into 1 plus psi delta theta divided by capital F. Now we will see at the time step equal to 0 hours. Between time interval between 0 to 0.25 hours. So we are seeing in between these two. So I'm going to represent it as first time step at t is equal to 0 hours. To 0.25 hours.
Sir, what is F here?
Infiltration rate. So this is between 0 to 0.25. You have an incremental rainfall of zero point 0.3 centimeter, zero point 0.3 centimeters. So what will be your cumulative rainfall in between this interval? So your capital F will be equal to your incremental rainfall itself. So we are seeing between the interval 0 to 0.25, and your incremental rainfall in that interval is 0.3. So that could be the water that can be infiltrated, but we need to check with the infiltration rate. So first what we will do is we'll find out what is the infiltration rate at this at this time interval. So we'll substitute the value 1.09 into 1 plus 2.1414 divided by zero point 0.3, which is equal to 8.87 centimeter per hour. So this is the infiltration rate which we found out. Now we are not sure whether this much amount of water infiltrated or not. We are just assuming that this much amount of water could be infiltrated. So now
Sir,
what?
this is a small f or capital or a small t.
Which one?
Sir, in the formula, before equal to.
This is F. This is F only. So now what we are doing is we are assuming that in the first time interval, zero point 0.3 centimeter of rainfall can be infiltrated, but we are not sure whether that is the rainfall that is infiltrated. So we are just substituting in the Green and Ampt equation and finding out what is the potential infiltration rate. So your potential infiltration rate is about 8.87 centimeter per hour. And if I calculate the rainfall intensity is nothing but your rainfall divided by time interval. So rainfall is zero point 0.3 and the time interval is 0.25 hours. So if we find out, it is 2.4 centimeter per hour. So your rainfall intensity is less than the potential infiltration rate. So F is equal to zero point 0.3 centimeter only in the first time step.
Sir, it is 1.2.
Uh, just a minute. Yeah, it is 1.2. Sorry. So this is 1.2 centimeters per hour. So we have found that your infiltration rainfall intensity is less than the potential infiltration rate. So from this, what we can say that in the first time interval, no ponding occurs, and your actual infiltration rate is equal to your rainfall intensity. So now we'll be repeating the same thing for all the other time steps. So we have so many intervals. We'll be repeating the same step. We'll be checking. First, we'll be assuming your F is. We'll be assuming your capital F. Then you'll find out your small f, that is your infiltration rate. Then you'll check whether
Sir,
it is.
isn't it take too much time to solve these questions, sir? If we solve like this.
Yeah, of course it will take time. Here why we are doing this to understand the concept. So you need to know the concept than solving the question. Then whatever the question comes, you can solve easily. So that is why we are doing like non-conventional questions. These questions will not come in the competitive exams, but it will help you to understand the concept.
Okay, okay, sir.
So now next time interval, is 0.25 hours to 0.5 hours. So here we'll be finding out. So your cumulative capital F will be zero point 0.3 plus zero point 0.4.
Sir, it will be added on.
Yeah, we'll be adding and we'll be finding out.
Okay, sir.
So this will be zero point 0.3 plus zero point 0.4, which is 0.7
7 centimeter.
centimeters. Now we'll be finding out. Again, small f we have to find out.
Sir, the K is constant here, like 1.09
Yeah,
every
that
time.
is 1.09 every time. So only thing that will be changing is the
F,
denominator. The
capital F.
Yeah, capital F will be changing every time. So this will be around 4.42 centimeters per hour. And now we'll be calculating what is the rainfall intensity again. So your rainfall intensity is equal to zero point 0.7 by zero point 0.5.
Sir, the difference is 0.25, or we take the difference of from 0 to 0.5.
This is 0.25 only. So here we'll be finding out the rainfall that happened in that particular time interval. So rainfall that happened is zero point 0.4 divided by 0.25, that will be 1.6 centimeters per hour. So here also you have the, so your rainfall intensity is less than your small f. So here also no ponding occurs. And
Sir, sir, in rainfall intensity, we are taking the value of only 0.4. That is the particular interval value.
yeah, because
But
the first rainfall ended already, right? So this is the next time interval.
in the infiltration rate, sir, we take the 0.7 as the sum of 0.4 plus
That is
0.2.
cumulative infiltration.
Okay, sir. Okay, sir. Got it.
Cumulative infiltration, that is we are adding it up, but rainfall intensity in that particular time interval we are just finding out what is the rainfall intensity. So here also your F actual will be equal to your rainfall intensity. Then we'll be moving on to the next time step. So that is at t is equal to zero point 0.5 hours to 0.75 hours. So here we'll be calculating again. F is equal to the previous time step we calculated F as 0.7 plus, here you are having another 0.5.
Sir, how we get to know that 1.6 is equal to the like FACT is equal to I? Sir, this is the value of I is equal to 1.6. But in the question, it is running.
See, in question what is given is incremental rainfall. So every time step you have this much amount of rainfall that is happening. So we are finding out the rainfall intensity. So we are dividing it by the time step and we find out what is the rainfall intensity. So in between the time interval 0.25 to zero point 0.5 hours, rainfall of zero point 0.4 centimeter occurred. So we are finding out the intensity of that rainfall, that is 1.6 centimeter per hour. And we
Okay,
are
sir.
comparing it with the infiltration rate. So if the rainfall intensity is less than infiltration rate, all the rainfall will infiltrate, right? So that is why
Yes, sir. Yes, sir. Yes, sir.
no ponding occurs, but actual rate of infiltration. What is actual rate of infiltration? That is the infiltration that is currently happening in the field, corresponding to your
That is
rainfall intensity.
0.7 centimeter.
Actual infiltration rate. This is rate. So F actual is equal to your rainfall intensity, because your potential infiltration rate, this we can call it as, I'm calling this as FP for now. So your potential infiltration rate is higher than the rainfall intensity. So your actual infiltration rate will be equal to the rainfall intensity. You are getting?
Yes, sir. Yes, sir. Getting, sir.
Yeah. So in the next time step, we are having cumulative infiltration rate as 1.2 centimeters. And now again we'll be calculating what is the infiltration rate. So your infiltration rate is equal to, again, 1.09 into 2.1414 divided by, here it will be 1.2 plus 1. This is equal to 3.035 centimeters per hour. And again we can compute the rainfall intensity. So that is 0.5 divided by 0.25.
That is 2.
So that is 2 centimeters per hour. So again your rainfall infiltration rate, rainfall intensity is less than the infiltration rate. So in this case also, no
No
ponding
ponding
occurs.
occurs because all the rain water is going
Yeah,
below the earth surface.
yeah. So F actual will be equal to the rainfall intensity. So now we can come to the next time step. So next time step is 0.75 to 1 hour. So 0.75 to 1 hour. So your cumulative infiltration is your previous infiltration plus next time step. What is the rainfall?
1.2 plus 0.6.
1.2 plus 0.6. That is 1.8 centimeters. Now again we'll be calculating the F. So 1.09 into 2.1414 by 1.8 plus 1. So this is equal to 2.386 centimeter per hour. And if we calculate the rainfall intensity I, 0.6 divided by 0.25, so 2.4 centimeters per hour. So you can see now what happened. Your rainfall intensity is greater than F. So we cannot assume F is equal to I into T. Okay. Now what we are going to do is we are going to find out what is the error that we are making by assuming uh, your F as 1.8 centimeter.
Sir.
Yeah.
Sir, we found infiltration rate that is 2.386.
Yes.
If we round up to one decimal, then it will be also 2.4 centimeter per hour.
Yeah, that is
Then,
what I'm going to tell now. So we are going to find out what is the error in the approximation. So if we see, we will calculate what is the rainfall excess in this time step. So rainfall excess is given by I minus F into delta T. So your rainfall intensity is 2.4 minus your F is 2.386 into delta T is 0.25. So your rainfall excess is 3.5 into 10 power minus 3 centimeter. So this, you can see this is a very small quantity. We can approximate it to 0 also. So in this time step, what we are concluding is rainfall excess is negligible, and we can assume ponding starts from this time interval. Okay. Now, now we got at point between 0.75 to 1 hour. So we know that ponding is occurring. So we can also estimate the ponding time in this case. So ponding time is given by the mean and Larson equation. So that is given by k psi delta theta divided by I into I minus k. So k is 1.09, this is 2.1414 divided by rainfall intensity in this time step is 2.4 into 2.4 minus 1.09. So this is equal to 0.742 hours. Okay. Now we are going to assume that since the difference is very small, we are going to assume ponding starts at time t is equal to 0.75 hours. Okay. Now the ponding has occurred. So after ponding, we are going to estimate the cumulative infiltration depth. Till now, what we were doing is we were finding this capital F by simply adding the incremental rainfall. Once the ponding started, we cannot further calculate it like that. We need to use the Green and Ampt equation to calculate what is the cumulative infiltration that is happening after the ponding. So for that, in the last class, ma'am would have derived an equation. So that is a iterative equation. So F at t plus delta t. So that is the cumulative infiltration depth for the next time step minus cumulative infiltration rate at the current time step minus psi delta theta into natural log of psi delta theta plus ft delta t divided by ft plus psi delta theta, that is equal to k into delta t. So this is the equation which we would have used. So we need to solve this.
Sir, this equation we have to use after the ponding once
Yeah,
gets
once the
started.
ponding started, we have to use this equation to solve. So now we'll be seeing what is happening at time interval 1 hour to 1.25 hours. So we need to find what is f of t delta t. So that is the unknown. So infiltration until the previous time step, that is equal to, we would have calculated in the previous time step, that is equal to 1.8 centimeter minus rest of the values are known values, 2.1414 into natural log, this is 2.1414 plus ft delta t is again unknown, divided by, this is 1.8 plus 2.1414, which is equal to k is 1.09 into delta t is 0.25. So we are going to compute what is the cumulative infiltration depth in this particular interval. So here if you see, uh, delta t is 1.25 minus 1, which is equal to 0.25 hours. So we are using this. So here we have to assume some value for f of t delta t. So I'm going to assume equal to this itself. Then we need to solve this equation. So your left hand side should be equal to your right hand side. Until then, we need to keep repeating this step. So you can solve this in your calculators. You can find out some video where you can solve iteratively one equation in the scientific calculator. So we will get f of t plus delta t as 2.354 centimeters. So this is the infiltration, cumulative infiltration that is happening at time interval 1 hour to 1.25 hours. Now we need to find out what is the infiltration rate. So we are going to check again whether the condition is still true or not. So F is equal to 1.09 into 2.1414 divided by 2.354 plus 1, and we'll get 2.08 centimeters per hour. And we'll be computing what is the rainfall intensity also in this time step. So in this time step, the rainfall intensity will be between 1 to 1.25. You are having a rainfall of 0.7 centimeters. So 0.7 divided by 0.25, this is 2.8 centimeter per hour. So again your I is greater than F. Ponding occurs. F actual is equal to F, which is equal to 2.08 centimeter per hour. So again we'll be going to the next time step. At t is equal to 1.25 hours,
1.25 to 1.5.
1.5 hours. So again we'll be finding out what is f of t plus delta t minus 2.354. This is the previous value which we found out, 2.1414 into ln 1414 plus f of t plus delta t whole divided by 2.354 plus 2.1414, which is equal to 1.09 into 0.25. So here we'll be assuming f of t plus delta t equal to 2.354, and solving you will get f of t plus delta t in this time step is equal to 2.851 centimeters. So again we'll be calculating the infiltration rate, that is 1.09 into 2.1414 divided by 2.851 plus 1. This will be equal to 1.908 centimeter per hour. And we'll be calculating what is the rainfall intensity at this time step. So I think the rainfall,
Sir, sir,
yeah,
sir, in the equation, if we assume that ft plus delta t is equal to 2.354, okay,
yeah.
sir, we can also put this value on the very first equation, that is ft plus delta t. Why didn't we put this value here?
So in this equation you are saying,
Yes, sir.
so why we are doing is when you are trying to solve something in your calculator, so we need to assume some close range, right? So
Close range in what?
like your calculator will solve based on the nearest range only. It will keep iterating, it will keep increasing the values.
This is
So you can in the previous equation also you can put whatever value you want. You can use instead of 1.8 here, you can give 1, you can give point 0.1, you can give point 0.5, you can give 5 also. Ultimately your calculator is going to give the answer which satisfies this equation only. But time, the amount of time it takes to give the answer, that will depend on how close you are giving it. So
Sir, my question is that, sir, here you have written that assume ft plus delta t is equal to 2.354,
yeah,
and you are putting this value on the just previous step equation.
yes,
Here, sir, here beside 2.1414 plus ft plus delta t.
yes.
Sir, if you are putting this value on here on this place, then why didn't you put this value on the very first step also, like ft plus delta t minus 2.35?
Here
Yes, sir.
you are asking why I didn't substitute here.
Yes, sir.
See, this is an implicit equation. So from this you cannot find out what is the expression for ft plus delta t. So if you see here, you cannot write a equation like this. Ft plus delta t is equal to something. We cannot derive this expression because you have a natural logarithm here, and inside that you have this ft plus delta t. Understood?
Okay,
So
sir.
when you
Okay,
are
sir.
going to solve in calculator, how we will write this equation is, so we'll be writing the equation like this. So x minus 2.354 minus 2.1414 into log of 2.1414 plus 2.3, sorry, this will be again x divided by
2.354 plus 2.1414.
2.354 plus 2.1414.
2.1414.
Okay, so
Yes,
that
sir.
will be equal to 1.09 into
1.09 into
0.25.
0.25.
So when you solve in calculator, we will give x equal to 2.354 centimeter. So this will be substituted here also and there also, and it will find out whether your left hand side and right hand side are equal. If it is equal, it will give the final x value, the value which satisfies the equation. So that is how your calculator will solve. But we are representing here as this equation. But when you solve in calculator, what it essentially does is it substitutes your initial guess in both of the places and finds out whether the equation is getting satisfied or not. Understood?
Oh, okay, sir. Okay, sir.
So you can, that's why I told you can search in YouTube like how to solve a implicit equation. So this is termed as implicit equation.
Okay, sir.
How to solve implicit equation in scientific calculator. If you use that, you will see, you can see how to solve this. So then you will understand why we are doing that.
Okay, sir.
So here the rainfall intensity is 0. 0.8 divided by 0.25, that is 2.4 centimeter per hour. So here also I is greater than F.
Sir, it is 3.2, sir.
Uh, sorry. Yeah, it is 3.2 multiplied by 4. Yeah. So it is 3.2, and here also your ponding occurs. Next, we'll be going to the next time step at t is equal to 1.5 hours to 1.75 hours. So f of t plus delta t minus, so your f, capital F at the previous time step
Sir,
was
sir, in question it is only given till 1.5, sir.
1.5. No, it is up to 1.75 to 2. Maybe you would have missed here.
Okay. My sorry, sir, my mistake.
So f of t minus delta t minus, in the previous time step we got capital F as 2.851 centimeter. Again minus 2.1414 into 1, 2.1414 plus f of t plus delta t divided by, here it is 2.851 plus 2.14, which is equal to 1.09 into 0.25. So if you solve this, assuming we will get f of t plus delta t as 3.313
Sir, we are
centimeters.
assuming this ft plus delta t from the previous value which we
Yeah,
have.
previous value. So why we are
Okay.
assuming is, your cumulative infiltration rate is always greater only, right? It will keep increasing
Yes,
with
sir.
time. So that's why we are assuming the previous time step value, so that your calculator can solve little faster. That's it.
Okay, okay, sir.
So f is equal to, we are finding out the f, 1.09 into 2.1414 divided by 3.313 plus 1. 1.794 centimeter per hour. So in this time interval, you can see one more thing is there. So your rainfall intensity is 0.4 by 0.25. It is 1.6 centimeter per hour. So what happened here? So your rainfall intensity is less than infiltration rate. So whatever value we are finding out for this current time step will not follow the Horton's, the Greenham's infiltration equation, but rather here it will be simply F equal to, so here what happened is your rainfall intensity is less than F, so no ponding occurs. But we have estimated F of t plus delta t based on green and Ampt equation. So that is wrong. So what we have to do is, in this time step, f of t plus delta t is given by ft. This is in the previous time step, plus I into delta t. Understood?
Yes, sir.
So ft plus delta t will be equal to, in the previous time step we found,
Sir, 2.85, 3.313
yeah, 3.313. So 3.313 plus 1.6 into
delta
0.25.
T. Yes, sir.
So ft plus delta t equal to 3.913 centimeters. So now we can calculate what is your small f in this particular time step. 1.09 into 2.1414 divided by 3.913 plus 1. So this will be equal to 1.68 centimeter per hour. Okay. Now
Yes.
the last time step.
To 1.75 hour to 2 hour.
2 hour.
Here we can T plus delta T minus.
So what is your rainfall intensity in the last time step? I think 0.6 divided by 0.25, which is equal to 2.4 centimeter per hour. But what we have estimated in the previous time step, it is 1.68 centimeter per hour, right? So again, what happens is your rainfall happens, then it suddenly decreased for one time interval, and in the next time interval, it again increased. So here, your I is greater than F, again ponding occurs. So again, we have to estimate by the green and Ampt equation, f of t plus delta t minus 3.913 minus 2.1414 into ln of 2.1414 plus f of t plus delta t divided by 3.913 plus 2.1414, which is
Is
equal
equal
to 1.09 into
1 to
0.25.
0.25.
So assume f of t plus delta t is equal to 3.913 centimeter.
Centimeter.
Solving, you will get f of t plus delta t is equal to 4.327 centimeters. So at the end of 2 hours, you can find out what is small f. So at the end of 2 hours, it will be 1.09 into 2.1414 divided by 4.327 plus 1. F will be equal to 1.629 centimeter per hour. And you can check with the rainfall intensity also. Rainfall happens is a 0.6 in the last hour divided by 0.5 is equal to, this is 2.4 centimeter per hour. So I is greater than F, ponding occurs. So now you
Ponding
can,
of
I will show you a graph. Uh, So this is visible now. So if you see here, I have plotted on the y-axis infiltration rate and rainfall intensity is there, and on the x-axis you have your time interval. So I have plotted the rainfall hydrograph and I have plotted the infiltration rate as per the Green and Ampt equation. So you can see at the 0.75 hours our ponding started. So your infiltration rate cuts your hydrograph, and it continues. And in one place again we saw rainfall intensity decreased, so we don't have any rainfall excess there. So all the water is infiltrated, and again at the last time step your rainfall intensity is more than the infiltration rate. So here in this graph there are three things which you need to remember. So until your point where the uh, infiltration rate cuts your rainfall hydrograph, whatever is the uh, rainfall that is happening is termed as initial abstraction. So that is your initial abstraction which is lost. And later what happens is the area under your infiltration rate curve, the rest of the thing shaded in the blue, they are called as continuing abstraction. So some water has already abstraction that has been completed, then continuing abstraction happens. So why it is called as continuing abstraction is that during this period your runoff also generates and infiltration also happens. So it is termed as continuing abstraction. So infiltration also happens, your runoff also happens simultaneously. But just before that particular time step, 0.75, only the infiltration happens, but there is no runoff that is happening. So now we can compute. So we have calculated capital F. So up to 0.75, if you sum it together, it will be around 1.8 centimeter. That is called as initial abstraction. Then from 0.75 to 2 hours, if you find the uh, cumulative infiltration depth, that you can term it as continuing abstraction. Then finally will be your rainfall excess. And
Sir,
summation of,
sir, the rainfall excess is that the ponding there is ponding occurs.
yeah, once your soil is saturated, your rainfall starts contributing to the runoff. So that is the rainfall excess. Until that point, whatever is the rainfall that is happening will be infiltrated into the soil. So there will be no rainfall excess. So once the ponding begins, your runoff starts to happen.
Okay, sir.
And summation of rainfall excess plus continuing abstraction plus initial abstraction should be equal to the rainfall.
Sir, if the question asks like that, if there is a rainfall occurred in time interval 1.50 to 1.75, then our answer should be 0 or anything else.
Your what is that?
Sir, if there is question asked that the runoff occurred in 1.50 to 1.75,
Yeah,
then our answer will be 0 or
yeah,
something else.
zero. It is zero.
0, yes.
Because everything is infiltrating. Your rainfall intensity is less than the uh, infiltration potential infiltration
Infiltration rate.
rate. So there
Yes.
is no runoff that occurs in that particular time step.
Okay, okay, sir.
So and summation of all this will be equal to your runoff. That is the final check you can make,
Okay, sir.
whether you have solved the question correctly or not, or you have missed something. You can find out. So your initial abstraction equal to 1.8 centimeters, and continuing abstraction. So what is this continuing abstraction? We have found out everywhere capital F only, right? So what
Yes,
we
sir.
can do is, for continuing abstraction, capital F at what was the time interval? Capital F until the second hour minus your initial abstraction. So f at second hour. So that will be the last value which you found, 4.327 minus 1.8, that is equal to 2.527 centimeter. So this is the continuing obstruction. Then what is your total rainfall excess? So total rainfall excess is total precipitation minus whatever that is infiltrated. So your total precipitation is 4.9. 4.9 minus 4.327, that is 0.573. So this is about the green and damp infiltration and calculation of ponding time. So next we'll move on to the next question. So in this question we'll be seeing how to find out the ponding time for a Horton's equation. So your Horton's model is given. F of t is equal to 1.2 plus 2.4 into e to the power of minus 2.5 t. Now we have to calculate what is the ponding time, and we need to if the catchment receives a rainfall intensity of 1.5 mm per hour. So this is the expression which is given in Venti Chow book. Now we'll see how to derive this expression.
Sir, the same question type will be asked in assignment.
Maybe not. The same question will not be there in assignment, I think.
Question type, sir, type, like type.
Yeah, similarly will be there. You will be calculating maybe ponding time for mean and Larson method. So this is way beyond what it has been covered.
Okay, sir. So the thing is that I have my classes from 9 to 5 continuously from in the weekdays, sir. So uh, I am not able to attend your classes from that is 4 to 6, sir.
Yeah, yeah, sure. No problem. Recorded videos are available. I will share the link at the end of the session. You can save that link.
Okay, sir. Thank you.
So now we'll be seeing question number 2. This is ponding time for Norton's model. So we know that infiltration rate by the Horton's equation is given. So infiltration rate by Horton's equation is f of t is equal to fc plus f naught minus fc into e to the power of minus kt. So this is the equation that is given. Now I'm going to rewrite this equation in a certain way. F of t minus f of c is equal to f naught minus fc into e to the power of minus kt. From this I'm going to find out two different equations. So I'm going to find out what is e power minus kt. So e power minus kt is equal to f of t minus f of c divided by f naught minus fc. So this is one equation, and I am also going to find out what is t here. So we are going to find out what is t. T is equal to minus 1 divided by k into ln of ft minus fc divided by f naught minus fc. You are understanding this, right?
Yes, sir.
So these two equations now we have found out. Now cumulative infiltration depth. So this is nothing but your capital F. So capital F at any time t is equal to integral of integral over t f of t dt. This is the general expression. Now I'm going to write the expression for the integrated version of it. Fc into t plus f naught minus fc divided by k into 1 minus e to the power of minus kt. So you are able to understand how this equation comes. This equation.
Okay, sir.
So we are integrating this equation. If I say this is equation 1, here I am integrating the equation 1. So without any limits, I am just integrating. That's it, nothing else. So what we are doing is we are integrating from 0 to t. So when you do that, you will get this expression. Now what I'm going to do is, we have found out the expression for t and expression for e power minus kt. So I will call this as equation 2, this as equation 3. Substitute 2 and 3. So I'm just going to substitute 2 and 3 in the above equations. So I will get f of t is equal to fc into minus 1 by k ln of ft minus fc divided by f naught minus fc plus f naught minus fc divided by k into 1 minus ft minus fc divided by f naught minus fc. So I have just substituted. Now I'm going to simplify this expression. So f of t is equal to fc into minus 1 by k into ln of ft minus fc divided by f naught minus fc. So I'm just going to take a LCM over here. So that will be f naught minus fc minus f of t plus fc. So here you can put a bracket divided by f naught minus fc. So here plus fc minus fc and these two we can cancel. So the remaining term will be f of t is equal to fc, here it is into product into minus 1 by k ln of f of t minus fc divided by f naught minus fc plus f naught minus f of t divided by k. So here k is common. I'm just going to take it outside. So f of t is equal to 1 by k into minus fc natural log of f of t minus fc divided by f naught minus fc plus f naught minus f of t. Understood?
Yes, sir.
So now we can come to the bonding condition. So at ponding, what happens? So at ponding, your small f of t is equal to I, and capital F of t can be written as I into Tp. Correct?
Yes, sir.
So now we are going to substitute the same thing in the above equation.
So where TP is rate of ponding,
Yeah, time of ponding.
time
So
of ponding. Sorry.
that only we are going to find out. So I into Tp is equal to 1 divided by k minus Fc, natural log of, instead of f of t I am going to put I minus f of c, f naught minus fc, and the rest of the things will remain the same, plus f naught minus, here also we will put I. So these are the places where we are changing. So this one will change, this one will change, and this one will change. So now we can find out the time of bonding. So this is the simple expression derived. 1 divided by intensity I am bringing to the right hand side into f naught minus I minus fc ln of I minus fc divided by f naught minus fc. So we have found out this is the final equation. So this derivation is not available in textbook. So now we have found out. Now in question we have been given as Horton's model is given. So ft is equal to 1.2 plus 2.4 into e to the power of minus 2.5t. So from this we can find out what is the parameters. So your fc is equal to 1.2 centimeter per hour, k is equal to 2.5 per hour, and f naught minus fc is equal to 2.4. From this we can find out what is f naught. F naught will be equal to 3.6 centimeter per hour. So this is the parameters. Now we can simply substitute. We know all the values, and in question I is given as 1.5 centimeter, 1.5 centimeter per hour. So we can substitute all the values in this above equation to calculate the time of ponding. One divided by 1.5 into k is 2.5 into f naught. This is 3.6 minus your intensity minus fc into natural log of 1.5 minus 1.2 divided by 3.6 minus 1.2. So the ponding time will be equal to 1.225 hours. So this is how you estimate the ponding time for Horton's equation. Now, what happens after ponding? That we need to know. How we will estimate the capital F. So after ponding, we can estimate capital F as something like this. Fc into T plus F naught minus Fc divided by K into 1 minus e to the power of minus K into T minus Tp. That's it. One small change. So after ponding, you can estimate the capital F like this. So before ponding, your f of t will be equal to I into T. So this is how we need to estimate.
1.8375, sir.
1.8. No, I just calculated. 1.5 minus 1.2 divided by 3.6 minus 1.2. Sorry, 1.2 minus answer minus 1.5 plus 3.6 divided by 1.5 divided by 2.5. I'm getting 1.225 only. Just check the calculation.
Sir, 1.225 is the time of ponding,
Yeah.
but FT is I into time of ponding. I is 1.5.
Oh, you are saying that. Okay, okay. I thought. Okay, that is not a part of the question. It is just I just added. So
Okay,
in
sir.
question we are just asked to find calculate the ponding time only. So you can calculate later.
Okay, okay, sir. That is 1.225 is the answer, sir.
Yeah, yeah.
Okay, thank you, sir.
So next we'll be moving to this is about infiltration. One more question is there. We'll see the phi index. So this is the SES curve number method. So this is an empirical method to determine the runoff from a catchment. So in this question, 600 acre of watershed is given. Is the watershed area, and curve number for the saturated moisture condition is estimated to be 70. So in this, if you say saturated moisture content, so it is corresponding to CN3, that is wet conditions, and the value is directly given as 70. Now we need to estimate what is the direct runoff volume for 4 days of rainfall. So in table rainfall for 4 days is given. We need to find out what is the daily runoff from this uh, catchment. The AMC is category 3, that also they are given. Use standard SCS curve number equation, and we also need to find out what is the runoff volume if the curve number value changes to 70, changes to 80. So we'll be seeing this is a very straightforward question. So date July 1,
July 2, July 3, July 4, 60,
rainfall is 60, 21,
21, 40,
40,
16.
60. This is a memo. So we know that SES curve number equation. So SES curve number equation. So your runoff can be written as P minus 0.2s the whole square divided by P plus 0.8s, provided your precipitation is greater than zero point 0.2 times of IA. Now, precipitation is greater than initial abstraction, that is equal to 0.2s. Okay, otherwise 0. So this is the only thing which you need to remember. So this is the most important condition. Only if your precipitation is greater than 0.2s, your runoff will be equal to this value. Otherwise, it is 0. So we will see. So first condition is when curve number equal to 70. First, we need to compute your maximum potential retention. That is yes. This is maximum potential retention. So that is derived from the curve number equation itself. It is an empirical equation. It is something like 1000 by Cm minus 10. So this will be in inches. So we'll convert to mm. So we'll be multiplying with 25.4. So this will be in mm. So we can find out 1000 by 70 minus 10 into 25.4. Your S will be equal to 108.6 mm.
Sir, 85.
Yeah, you can round off. That is not an issue.
Sir, that is the issue in the assignment, sir.
So in this case, you be careful. Like we are just rounding it off here. While you do with 2 or 3 decimal points.
Okay, sir.
So now we are going to calculate what is your initial abstraction. IA is equal to 0.2 times of S, 0.2 into 108.6, that is equal to 21.78. So now you can write the runoff equation. So Q is equal to P minus 0.2S the whole square divided by P plus 0.8S only if P is greater than 21.78 mm, 0 otherwise. So it's always good to write this equation, otherwise we will forget. So now we can form a table, date, then precipitation, Q. So you can compute, I have already computed. So July 1, July 2, July 3, July 4. First day is 60, second day is 21, third day is 40, and fourth day is 16. So your precipitation should be greater than 21.78 mm. So in all the other places you can directly put 0. So these two places no runoff happens, and only in the rest of the other days runoff happens. So this is equal to 9.93 and this is equal to 2.61. So it is just direct substitution in this above equation. See, if you substitute for second condition, P is equal to 21, you will still get an answer. You will not get a negative answer because you have a whole square here. So since you have a power of 2, although P minus 0.2s is negative, you will get a positive answer for runoff. It doesn't mean that you have runoff there. So you have to be very careful in this particular question. So now we can make a summation. So since we have to find the volume, we need the what is the total runoff. Sum is equal to 12.54 mm. Now we have to determine what is the volume of the runoff. Volume is equal to runoff depth multiplied by area of the catchment. So volume is equal to 12.54 into 10 to the power minus 3 into 600 hectares. Hectares to meter square is 10 power 4. So 1 hectare is 10 power 4 meter square. So volume is 75240 meter cube. So this is the volume of runoff. So generally you will be asked to express in terms of million meter cube. You can just divide by 10 power 6. So that is the usual unit. Now part B of the question is, when curve number equal to 80, what is the total runoff and the total volume? So when curve number equal to 80, date, first we need to find out what is S, maximum potential retention. That is 1000 by Cn minus 10 into 25.4, which is equal to 1000 by 80 minus 10 into 25.4. So maximum potential retention in the second case is 63.5 mm. and the initial abstraction is 0.2s, which is equal to 63.5 into 0.2, which is equal to 12.7 mm. So now again we can calculate date, precipitation, runoff. So precipitation is 60, 21, 40, and 16. And if you compute, for this case, your precipitation is greater than 12.7 in all the cases. So all events will generate runoff. So again, we are taking a sum. Volume So this is the volume generated in the second case.
Got it, sir.
Okay, we'll see one more question related to your curve number. So here we need to compute the runoff hydrograph from, that is the excess rainfall hydrograph from total rainfall is 136.144 mm on a 500 acre watershed. The area comprises of 50% of cultivated land with the hydrologic soil group C. So 50% of 500 acres consists of a land with a curve number of 88, and 30% is residential complex, and that 30% has a curve number of 90, and the remaining is forest land, and the curve number for the forest land is 66%, and incremental precipitation is given. So we have time and we have incremental rainfall that is happening in each hour. Now again we have to plot what is the cumulative rainfall, initial abstraction, continuing abstraction, and the rainfall excess. So our main aim is to find out what is the excess rainfall hydrograph. Rest of the other things we can see how it just varies according to the time. So till now we have seen that curve number was given, but now we need to find out from a watershed. You will have different land use. Some will be forest, some will be water body. Then you will have urban areas. Then you will have agricultural lands. So we need to find out a kind of weighted average curve number for the catchment. So first we'll be determining what is the weighted curve number. Then we'll move on to finding out the runoff. So we'll see how to approach this question. So first we need to find out the weighted curve number. So Cn weighted is equal to, so 50% of the area, so I'm writing it as 0.5, has a curve number of 88%, plus 30% of the area has curve number of 90, plus the remaining area has a curve number of 66. So total area is 100%, so I'm writing it as 1. So if you compute this, weighted Cn is equal to 84.20. So for the rest of the calculation, we will be using only this curve number.
Sir, this is a generalized formula.
Which one?
Mm,
Yeah, weighted average.
okay, okay, sir.
So you will see in Thiessen polygon also you would have seen, no? P1A1 plus
Yes,
P2A2.
sir, yes. Yes, sir.
Same, exactly the same formula. Just here
Okay,
it is in terms of a percentage. That's it.
okay, sir.
So here the maximum soil retention. So once we find out curve number, we can find out what is the maximum soil retention. That is S is equal to 1000 by curve number minus 10 into 25.4. Once we find this, we need to find the initial abstraction. That is 0.2 times of S. That is equal to 0.2 into 47.662. So your IA is equal to 9.533. So now we can see how the whether runoff happens or not. We can check it out. So first I'm going to write what is the time interval and rainfall. So 0, 1, 2,
3, till 7.
5, 6, 7, 7. So first it
0,
is 0, then
5.08,
5.08,
17.78,
7.78, then
9.398,
9.40.
398 it is given, sir.
Okay, I might have approximated. Okay, let it be 9.398. Then you will have
26.416,
416. Then
59.436,
436. Then
16.256,
256. Then 1.7.
1.778.
Okay. Now you can compare your initial abstraction and your rainfall. So I'm just going to circle it out. So this, and this. So these three time step, your runoff will be 0. So for rest of the time step, you need to calculate the Q. So first I'm going to compute what is the cumulative rainfall.
Sir, in these three, the runoff will be zero because the rate of intensity is greater than all of these increment values.
No, no, no. Here it is 0 because runoff happens. If you see the SES curve number equation, Q is equal to P minus 0.2s the whole square divided by P plus 0.8s. This equation is valid only when precipitation is greater than 0.2s. Okay?
That is IA.
Yeah, that is IA. Your precipitation should be greater than initial abstraction. So what is initial abstraction? It is the water that is lost, right?
Yes, sir.
So if your precipitation is not greater than your initial abstraction, then your runoff will not happen, right?
Yes, sir. Yes.
But if you substitute your precipitation value here, so if you substitute 1.78 here in this equation, you will still get value for Q because here it is square. So 1.78 minus what is the infiltration initial abstraction 9.533. That will be minus 8 something, right?
Yes, sir.
So minus 8 the whole square, it will still give you the runoff value. It is a positive value.
Yes.
So that's why we have this condition. This condition is very, very important. So this condition we should not forget. If it is not there, then zero otherwise.
Yes.
So that is why we need to be careful with the SES curve number method. So now I'm just going to calculate the cumulative rainfall. So we are going to plot everything. That's why I'm calculating 5.08. This is I'm approximating a little bit. So that's what I have. 32.26. If I calculate, this is 58.67, 118.11, 134.37. This is 136.14. So I have just calculated cumulative rainfall. Now, next step is we are asked to find out what is the initial abstraction separately in the question. So we'll find out what is the initial abstraction that is happening in our catchment. So we have found initial abstraction.
So it is 9.533.
So
533
9.533
mm.
mm for the total time period. Zero to 7 hours. Now we need to find out what is the variation. So for every hour, what is the initial abstraction that is happening. So for that, we can see the rainfall table. So in the 0th hour, there will be nothing. So I'm going to write, I'm going to include a new column here. That is cumulative abstraction. So we are going to find out what is the cumulative abstraction. So in the 0th hour, there is no rainfall, so no abstraction. In the first hour, we will have 5.08. So whatever is the rainfall that is happening, that will be equal to your abstraction.
Cumulative rainfall.
Yeah. So that will be equal to your abstraction. So for the so at time t is equal to 1 hour. So your rainfall is 5.08
08
mm,
mm.
and your so what will be your initial abstraction at first hour? 5.08 mm.
5.08 mm.
So what is the remaining abstraction that is to be satisfied?
0.
Remaining, 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 whatever is remaining. So total is 9, right?
Yes, yes. 9.5
9.533
minus
minus
5.08.
5.08.
9.5 minus
So remaining initial abstraction is
4.473.
yeah, 4.473 mm. So this will be satisfied in the next hour. So if you see,
From hour 1 to 2.
yeah, so from first hour to second hour, whatever is the rest that will be satisfied in this time interval. So between 1 to 2. Remaining abstraction will be satisfied. Okay. So in the second hour, everything will be satisfied because your rainfall is 17.78 centimeter, 17.78 mm. So remaining will be around, if you subtract 4 point something, 13 mm of rainfall will be remaining. So so in the second hour, all the cumulative abstraction will be satisfied. So once 9 mm is satisfied, for the rest of the hours there will not be any initial abstraction. So it is, since it is cumulative,
All will be satisfied.
all will be satisfied. We can just write 9.533 everywhere. So next, what we need to calculate is, we need to calculate what is the continuing abstraction. So continuing abstraction is, your rainfall excess is also happening, that is your runoff is also happening,
Sir,
and your infiltration is also happening.
sir,
Yes.
sir, from 0 to 1 hour, there is also a runoff is 0, and from 6 to 7 hour, there is also runoff is 0. Then why we are calculating cumulative abstraction and cumulative rainfall?
Yeah, your runoff is zero, but you will see when you plot, I will show you the plot of the graph. Your at that time your runoff will become horizontal, so it will be in the previous time step, what is the, whatever is the rainfall, whatever is the runoff, the same runoff will be in the next time step also.
Okay, sir.
So we'll be seeing that. So now we need
Okay,
to
sir.
calculate what is the continuing abstraction, that is the cumulative infiltration. So in the first two time steps, cumulative infiltration is zero, because that is part of initial abstraction. Understood, right?
Yes, sir.
And from the second hour, your infiltration starts to happen. So in the derivation of curve number equation, we will be having a term called as FA. So I will write the equation first. So how we derive the curve number equation is, initially we'll be starting with the ratio like this: FA divided by S is equal to PE minus PE divided by P minus IA. That is ratio of actual retention to the potential retention is equal to direct runoff
Upon runoff
upon
minus initial
runoff minus
abstraction.
the initial abstraction. So this is the hypothesis by which we will be deriving the equation. Now, this FA is nothing but the infiltration that is happening. So we are going to compute this FA for every time step. So while derivation, we will be writing. So while deriving at one step, we will be having this equation: S into P minus IA divided by P minus IA plus S. So while deriving the equation, we'll be ending up with the equation like this. So I'm writing it directly. And so for every time step, we will be uh, finding out this equation. For all the time step, we need to find FA. So once we compute that, we will be getting cumulative infiltration. So for every time step, I have computed already.
Got it, sir.
Now, once we have the cumulative infiltration, we can find the incremental infiltration also. So that is incremental infiltration is nothing but the difference between these two. First time step it will be 0, second time step it's 0, then 10.4. Now we need
Sir,
to
difference between which one, sir?
difference between the cumulative infiltration. So these two.
Okay, okay, sir. Okay, sir. Okay, sir. Got it. Got it.
Now next is rainfall excess, cumulative rainfall excess. So your rainfall excess can be written as, your PE can be written as precipitation minus initial abstraction minus the continuing abstraction. So for all the time steps, find out PE. So similarly, I have calculated for all the time steps, and I have cumulated it based on the rainfall that is happening. So it will be 0, 0, here it will be 2.91, 7.34, 24.96, 75.47, 90.36. Again here also it will be 90.36 because we don't have any rainfall excess. So rainfall is less than your initial abstraction. So at the last time step you will not have any excess rainfall. And we can also calculate the incremental rainfall excess. This is in amount. So again incremental is the difference between these two. So this will be 2.91, then 4.43, 17.62, 50.52, 14.89, and here it will be 0. Okay.
Okay, sir.
So now we have found out all the things that is asked in the question. Now I will show you the graph. So here we are going to plot variation of cumulative rainfall, initial abstraction, continuing abstraction, and the rainfall excess. So this is how the plot looks like. So blue color is the cumulative rainfall. So it starts from 0 and continues, and it becomes horizontal at the end. And similarly, your initial abstraction uh, is the pink color line, and cumulative infiltration is green color, and red is the rainfall excess, that is the runoff. So this is how it varies in the each time interval. And if you plot this so if you plot this with respect to time, this is your plot of excess rainfall hydrograph. Plot rainfall excess versus time. So this is your excess rainfall, and this is your time. So first 2 hours there will not be anything, and in the last hour there will not be anything. In the rest of the time interval, you have the excess rainfall. So I have plotted that also. In the last time step, excess rainfall is 0, but it has to be corrected. That is a small mistake. I think there was some value in that. It is 0 actually. So this is the excess rainfall hydrograph.
Sir, from 6 to 7 or 7 to 8? 7 to 8, there is no nothing, sir.
Yeah. 7 to 8, there is nothing. That is a small mistake. I think I have to correct that. So rest of the things are like fine. So in the 8th hour, you will not have any runoff.
Okay.
That will be 0. I'll correct that and upload.
Okay, okay.
So this is the last question. This kind of question is highly expected in any competitive exam. So you can see this is the most difficult question which they can ask in the with respect to phi index.
So we are going to do it now.
Yeah, it is simple only. It is difficult because the concept behind it is a little bit detailed. So I will explain. So hydrograph for the given storm event happens for a total duration of 180 minutes. So your rainfall happens for 180 minutes at the time interval of 30 minutes over a catchment. The infiltration rate of the catchment initially before the start of the rainfall was 7 centimeter per hour, and this infiltration rate gradually reduces to 4 centimeter per hour after 1 hour of the start of the storm event. And in the next 1 hour, it linearly decreases from 4 centimeter per hour to 3 centimeter per hour. And in the last 30 minutes, the infiltration rate further decreases from 3 centimeter per hour to 1 centimeter per hour, and thereafter remains constant. And we need to find out what is the phi index, total infiltration, and the rainfall excess. Now you can see why it is difficult. In all the phi index questions, what you will be given is just the rainfall hydrograph, correct? In the question, you will be given only the blue color columns.
That is rainfall hydrograph.
That is rainfall hydrograph. And you will be asked to estimate what is the phi index for the given rainfall hydrograph, and the runoff depth will be given to you. Like if total rainfall is 10 centimeter, runoff is 3 centimeter, find out what is the phi index. That is the simplest question. Here what they have given is, instead of giving the runoff depth directly, they have given the infiltration rate, and that also infiltration rate is varying like this. It is not a straight line, or it is not a simple curve. From 0 to 60 minutes, it is decreasing from 7 to 4 centimeter per hour, and from 60 minute to 120 minute, it is decreasing from 4 centimeter per hour to 3 centimeter per hour, and from 120 minute to 150 minute, it is decreasing from 3 centimeter per hour to 1 centimeter per hour, and later it remains constant. So using this information, we have to find out what is the runoff first. So what we will be doing is, we will calculate the area under this infiltration rate curve, and we'll find out the total precipitation depth. If we subtract that, we will get the runoff depth. So first we will do that. So you are given a, so I'm just drawing it not to the scale, just to represent. So it varies something like this. So what we will do is we will find out the area under this curve. So we'll find out this hatched portion. So that is the total infiltration. So area under that is so your first block is 2 into, so that is the area of the rectangle. So I'm just going to write for the first 2 time step it is area of the rectangle, and for the last time step also area of rectangle. So 2 plus 4 into, each rainfall is happening for 30 minutes. So into 30 by 60. So this is in
300, sir.
so this is in centimeter per hour, and this is in hours. 300. No.
3, sir. 3.
Huh.
Sorry.
So next thing is, so this looks like a trapezium, right? This block.
Which one, sir?
This one, which I have marked in violet.
You said look like trapezium.
Doesn't look like trapezium, huh?
Yes, sir. Some of parallel sides half into height.
So this is A, this is B, this is your height. Sum of the parallel sides into height, right?
Yes, sir.
So I'm going to calculate the area of the trapezium. That is half into A plus B. It varies from 4 to 3 into height is total of 60 minutes. It is changing into 60 by 60. So each time step is 30 minutes.
3.5 plus 3.
And next, this is also another trapezium. Oh God. So let's see. Uh, what's that? So this varies from here to here. So this is also another trapezium. This small pink. This shaded portion.
Yes, sir.
So that varies from 3 to 1. So if I calculate that, plus half into, varies from 3 to 1, but it varies from in 30 minutes itself. So that is 30 by 60. And the last one is rectangle. That is 1 into 30 by 60. So if you compute this, your total infiltration is 8
8.
centimeters.
8 centimeters.
And we can calculate the area of the hydrograph, total precipitation. So that is P is equal to 11.5 centimeters.
Got it, sir.
Okay.
Yes, sir.
Now what is runoff? Runoff is equal to total precipitation minus infiltration, 3.5 centimeter. So R is equal to 3.5 centimeter. Now we got all the required data to calculate the phi index. Now next is the calculation of a phi index.
Where's your question?
So this is 2, this is 4, this is 5, this is 8, this is 3, and this is 1. Now I will tell you one simplest way to calculate the phi index. So in questions, in many of the things will be assuming. First, you will be assuming somewhere in the between 1 to 2, 2 to 3, like that. So I will tell you one simplest method to calculate. So if this is 1, 2, then 3, 5, and so on up to here you have 8. So now what we know is, we know that the runoff is 3.5 centimeter. Now I'm going to find out the area of the least intensity blocks. So these are all the intensity values. So I'm going to calculate the area of the least. So let me take the area of this plus area of this plus area of this. So just calculate the area. So that will be 2 plus 3 plus 1 into 30 by 60. This equals to 3 centimeters, right?
Yes, sir.
Now we have runoff as 3 centimeter and 3.5 centimeter, and if we eliminate these 3 blocks, your runoff will be equal to 3 centimeters. Now we are short of 0.5 centimeter. So what we can do is, we can directly assume your phi index between 3 and 4. So I will assume my phi index between 3 and 4.
Sir, why in between 3 and 4?
Yeah. See, our runoff is 3.5 centimeters, right?
Yes, sir.
And if you see the equation of phi index, your precipitation minus phi t should be equal to runoff, right?
Yes, sir.
So I am doing is, I am calculating what is this phi t basically. So this blocks which I eliminated, 2, 3 and 1. So I am subtracting from the precipitation, and if I do that, I end up with 3 centimeter. But we are short of 0.5 centimeters, right?
Yes, sir.
So our runoff should be 3.5, but we are only having 3 centimeter. So
Yes.
you can eliminate these 3 blocks, and in the next successive interval, you can assume your phi index. So between 3 to 4, if you assume, you will get your phi index directly without doing any trial.
Okay, sir.
So that is why we are assuming
Between 3 to
between
4.
3 to 4. So we are assuming phi index is here. So in one step, you will get your answer.
Okay, sir. Okay, sir.
So you don't have to do any trials.
Okay, sir.
So if we calculate, that will be, so whatever the blocks it is cutting, we have to take. It is cutting 4,
458.
yeah, 4 plus 5 plus 8
Yeah. 17.
into, you need to remember we have a 30 by 60 here,
That is 8.5.
minus 5 into, how many blocks it is happening? 1, 2, 3. 3 blocks into 30 by 60, which is equal to your runoff depth. So what is the value we are getting? 4 plus 5 plus 8 into zero point 0.5 minus,
So is it 3.33?
yes, it's 3.33. So if you solve this equation, you will get 5 is equal to 3.333 centimeters per hour. So how to check uh, whether it is correct or not? So simply we can check like this. So you can do an inverse calculation. 5 into delta t plus whatever the blocks which you eliminated, you can add them up. So 2 plus 3 plus 1 into 30 by 60, which is equal to, should be equal to your total infiltration. So this will be 3.333 into, it happens for 3 blocks of 30-minute time interval, plus this will be 2 plus 3 plus 1 is 6. This is 3. This is equal to. So this is equaling to 8, right?
Yes, sir. 8. 7.999.
Yeah. So whatever phi index that you calculate, it should be equal to your infiltration that is happening. So the main concept is why we are assuming phi between
3 to 4.
3 to 4
Because we
centimeter.
remain of only 0.5 centimeter.
So you should, in the questions, first you should see, you eliminate 2 or 3 blocks and you calculate what is the value that you are eliminating. So if it is just close to your runoff, you stop at that place and you assume the phi index between that, the, you need to find out what is the maximum of what you are eliminating. So here maximum what you are eliminating is 3, and
Yes.
just between 3 and the next highest intensity, you can assume your phi index.
Okay, sir. Got it, sir.
So that is how you can solve this question quickly. And a similar question has been asked in 2019 gate examination. You can refer to that question also.
Okay, sir.
You can try to solve it.
Okay, sir.
Yeah. So this is the end of today's session. And
Okay.
you asked for that channel